So one, and go back to Bayes' rule and conditional dependence and independence. You may say that most of the underlying foundations of this class is Bayes' rule and different versions of Gaussian distribution. Good question. So Kyla asked if we recorded the week 8 lecture on Wednesday. I believe the answer is yes. I've even put it, I did remember to put it on YouTube, I believe. So it's certainly on the Teams channel. Let me just check. YouTube is learning. It's a bit slow. Yeah, I did. Right. Okay. I am seeing an entry called Laplace and approximation and GP2 in the YouTube playlist. That means it's certainly on Teams too, because that's where I got it. So I hope that helps. And I think, yeah, I probably uploaded it 2 days later rather than the same day as I usually do. Hope that helps. Yes, so I left XKCD where it forces me to think whether this is really an application of Bayes' rule and whatnot. Turns out that yes, Bayes' rule is quite universally applicable, but you don't need to plug it in all the time. Oh yes, right. In Teams, sometimes it's buried in our Q&A. Teams decides to put it at some random spot in the chat log. Yeah, there's also a Teams folder where you can go in and see all of the recordings. If you don't know how to find that, post, like, ask a question somewhere, and I'm sure we'll point you to the right direction. So for this today, Wednesday, and next Monday, we're going to spend 3 lectures on chapter 8. This is, well, you could say an exorbitantly long time, given how much we've often spent like just one lecture on a whole chapter. And you may ask why. It is because graphical models, basically, it's a different way about thinking about modeling. And the main goal is to be able to model complex phenomena involving many different random variables. So remember, in linear classification and regression, we can have many different inputs, but we just kind of said, look, they're input, and we treat them all the same. We usually don't explicitly distinguish one input from the other. And when there are multiple output, we kind of just say, well, these are just multi-target regressions, and you just add more neurons to the neural net output unit and so on. And we also don't treat them separately. We can learn different ways for them, but that's about it. For graphical models, this is the structure within input and output are given more careful consideration, as we will see. So we'll start today by defining what it is, going through some notations, and then we'll talk about this important concept called conditional independence and deseparation. At the end of the new content, we'll briefly talk about quiz 2. Answer any of your questions. We'll basically talk about the histogram that already posted on Piazza and question number 4, which seems to stump lots of people. Okay, Fei Yang's question. Can I flag that to reply later? Because I'm not sure I can do the complete context switch back to the generalization lecture and back. So yeah, do remind me at the end if I forgot to get to this one, right? So one motivating scenario for taking into account, let's say, input variable dependencies is, let's say, image segmentation. For those of you taking computer vision or have taken computer vision, you will know. For the rest of you guys, we could think about image segmentation task. In fact, right, the field of computer vision started by working on simple images, because those are idealistic. We can manipulate the input and we know what the output should be. So if we have an image like this, a darker circle on the lighter background, we can just cluster the pixels and get perfect segmentation. But of course, real world photos are not like this. If we look at this picture, the two horses or ponies, depending on specialty of your horse knowledge, and we would like to segment the foreground and background. Please note, this is also a super simple, let's say, natural image, because the foreground object, there are two of them, and they are almost the same color. And then there's the background, it's almost the same color. Even that, if we cluster just the pixels using k-means, as the book illustrates in its k-means section, that it doesn't quite work, right? Because for the lighter colored pixels, it tend to group the highlights on the horse's body with the background of the grass. That's not great. So you can, you may say, oh, hey, we're using the wrong input space. For example, like the color space, like brown is clearly separated from green. You tweak the input space. Yes, that's one source, but we would like to segment images in general. One useful heuristic is the surrounding pixels should have the same label, right? So the one way to say that this is probably a wrong segmentation is because this surrounding pixels were classified as foreground, but these few pixels are classified as background. That's not great. And in order to do this, one way is to treat, say, each pixel. So we know that we can think about pixels as lying on a grid, because that's how imaging devices work. Right, and then we can try and enforce that the surrounding pixels get a label, whether label is foreground or background, being similar. Right, and you can do this with graphical models. Specifically, we'll talk about this one, like Markov random fields, on Wednesday. So the general motivation here is to encode independence and probabilistic dependence and independence relationship in the input and output variables. Moreover, in this particular section, or in chapter A, we don't distinguish input and output variables so clearly as in the regression classification case. So which variable is input and output are represented implicitly by, basically by conditioning. And things that are not observed are called latent. When we do inference on them, they become the output. Right. So here is, let's say, a first very simple classic textbook based network or graphical model. So it has 4 variables, and all of them are Boolean, or basically binary valued. They take values between true and false, right? Whether it's cloudy, yes or no. Whether the sprinkler is on, yes or no. Did it rain today, yes or no? And whether the grass is wet, yes or no. True and false. So this particular structure of the network sort of encodes our real-world intuition, common sense knowledge about this situation, right? So when the grass is wet, it could come from 2 sources. Either a sprinkler is on or it has recently rained. So either of these two variables in turn depend on whether it's cloudy or not. One is decided by nature, the other one is decided, let's say, by the owner of the house. The cloudy, they may be less likely to turn a sprinkler on. And the wet grass does not directly depend on whether it's cloudy or not, because being cloudy is not a source of water. Right? So let's just walk through this example, and then we'll talk about the general definition of a graphical network. Right. So for these 4 binary random variables, you can see that for any given day, these could be true or false, right? We can see that, well, this place is probably not Canberra, because the cloudy doesn't depend on any of these other variables. The Earth gives you a random draw, say, randomly pick a day, and the probability of cloudy is 0.8. That's not good. In Canberra today is quite sunny, and most of days like this. So let's say this is somewhere in England. And then given, then the next conditional probability is probability of the sprinkler being on and off, given whether it's cloudy or not. This corresponds to this particular table, right? P of S, you can see, where it's a 2 by 2, where the variable of sprinkler is true and false, and cloudy is true and false. And we can see that when it's not cloudy, the sprinkler is on with half a probability. When it's cloudy, the sprinkler is off with 0.9 probability. So that's sensible. Similarly, we have probability of rain given cloudy. And then at last, we have probability of wet grass given rain and sprinkler. So some expert have, when I wrote down these probabilities, they might not be 100% accurate, but they should be in the, like, represent some sort of real world knowledge. So the mission of chapter A is to basically teach us the language on how to write these conditional probability tables along with the graphs, and how to do inference on them, and indirectly learning on them. So you may say, what did we just do? Why are we doing this? There are 4 random variables. We can just write, in theory, the full joint distribution table, right? Indeed, we can. There are 16 states, and we can specify this full joint distribution using 16 numbers. Yes, that is valid. And in fact, this basically fully general joint distribution, according to Bayes' rule, right? Since we said cloudy comes first, we can always take that out and then condition everything on it. And then we can decide to, for example, condition rain on cloudy and then sprinkler on rain. So this is how Bayes' rule works. Right, we can have 2 arrows pointing to sprinkler, and then we can have essentially 3 arrows pointing to wet grass. This is completely valid. So this has 16 parameters. In contrast, how much parameters did the previous page have? It has 2 plus 4 plus 4 plus 8. You may say, oops, it actually did not save any parameters. That is true. Although in high dimensions, we are likely to save a fair bit. The argument for using factored distributions is that, for example, probability of rain given cloudy is easier to measure. You don't have to sit in front of that particular lawn and just record occurrences of all 16 type of events, you could just, for example, estimate PR given C using the weather report, right? Okay, we'll talk about sparsity and why we need a graph a bit later on. So here is a recap of what we just said. If we don't try and motivate or encode domain knowledge in independence of statistical independence of variables, we essentially end up with graphs or like the full unrolling of Bayes rule like this. If we would like to compute the probability of the grass being wet, we essentially marginalize out all of the other variables by essentially conditioning on the variables one at a time. If we have additional independent structure, on the other hand, we could factorize in a number of ways, right? So, this particular conditional probability has got simpler, this one has got simpler, and then the marginalization is done in 2 steps rather than everything has to be done together. So after walking through one example, here is what is called probabilistic graphical models and different types of graphical models. Right. So the nodes in a probabilistic graphical model are random variables. So we're talking about graph representations here. It's a graphical model. It's basically representing like a joint distribution is getting turned into a graph. There are different types of graphs. So there are, so from your, I think, discrete math or CS 101 or graph theory class or algorithms. So we can have directed graph, undirected graph, and also the factor graph is bipartite graph. And the edges represent probabilistic relationships. Depending on which type of graph it is, the relationship can be somewhat different. And the goal of making graphs like this is to capture structures in a joint distribution, which is what we said in the beginning. So today we're going to spend all of an hour and a half look at Bayes networks, also called directed graphical models. They express causal relationship between variables. So yes, it has an intimate connection with causal inference, but we're not going to get there in this class. The causal inference is a big subfield in machine learning now. There's a lot of exciting work happening there, but knowing Bayes network will give you some language to understand the basics of causal inference, such as dual calculus and so on. We are not going to get there and not going to hold you responsible for formal causal inference. For this class, you are responsible for reasoning about conditional independence. So again, as a pattern of in this machine learning class, we've been calling out 2 types of tasks: inference and learning. So for graphical models, the inference task is to compute the posterior distribution of one or more subsets of nodes, given values of some subset of nodes. In here, we assume the graph is known and also the parameters are known. Like so implicitly, so these are the input variables and these are the output variables. You can think about them like that. In graphical models, these sometimes have different names. So these are nodes we condition on, the outputs are the nodes are latent, and so on. Sometimes nodes are latent, but we don't care about computing their distribution, and that's also okay. in that case, they need to be marginalized out in different ways, as we will see. So the learning task for graphical models is to estimate the parameters. Basically, the conditional probability table we saw a few slides ago, basically. Estimating these tables is called, the task is called learning. And from a data set of observed values. So the implicit assumption is the graph structure is often known. I think this class is used to, I guess, learning task where we estimate parameters of regression and classification. So we know that, for example, we can do gradient descent on those. So you can think of estimating if the probability table is pre-specified, we just need to estimate the value. That's doable. But searching over graph structures, it's a big combinatorial search challenge, which we did not touch upon. We didn't talk about model selection almost at all, except in your homework 2 second problem question here. But let's say that. So yeah, the easier learning problem is that the graph structure is known. There are lots of heuristics and strategies for searching over graph structure, of course. You're not going to be responsible for them. In fact, for this class, I would say that, for example, for the exam, we're going to ask you about inference and not about learning. And that's enough to worry about. Okay, and also that is to say that once we master the techniques for inference in graphical models, the learning, the step from inference to learning is a much smaller step to take, which I'm fully confident that you guys can do it. You can master it yourselves after this class. So here's another recap of why we need graphical models, probabilistic graphical models. So the graph provides a simple way to visualize the structure of a probabilistic model that can be used to design and motivate new models and to audit this current model. So for example, there has been lots of manually designed models in medical diagnosis. There are different factors affecting a diagnosis and test results. They all become variables. You can see these gets quite complicated if the health condition gets a bit complicated. There are also a few famous models for example, debugging a printer, right? Why the printer is broken has many different sources, and they themselves have varying level of dependencies. For example, whether there's enough ink, there's enough paper, whether the different units in the printer is functioning correctly, whether the network is functioning correctly, and so on and so forth. Some of them are easy to observe from outside the printer, some of them not. You have to take the printer apart. If you're a network admin, let's say for the ANU, and you try to debug the hundreds of printers around different buildings, just imagine what you need to do, right? So you could express that problem as a probabilistic graphical model. So we could, from the graph, directly read off properties of the model, including conditional independence, from the graph alone. And in this class, we're going to do this before we end. Right? The second half of the class is that. So complex computations, such as performing inference in sophisticated models, so it can be expressed in terms of graph manipulations. So basically, graph provides as a way or a language to break down large inference tasks into smaller pieces so that we can tackle them, right? And if we use graph manipulation to perform inference, the underlying mathematical expressions are actually carried along implicitly, as we'll see next Monday. Okay, so if we have two nodes, we can only have, I don't know, a directed edge pointing either way. In fact, we saw this in the mixture model section without calling attention to graphical models. But a simple graphical model can be three nodes, right? A, B, and C. And they can have some arrows pointing to themselves, among themselves. So if we apply Bayes' rule, we can say that, oh, P of C, the joint factors into P of C conditioned on A and B times the joint of A and B. And we can say that, oh, B can further depend on A, and this is basically, we can write this expression in 8.2. What this two example shows is that we can have a graphical model, but it does not simplify anything. Because the expression of conditional probability is the same as the Bayes rule, as if we did not have this graphical model. But why are we looking at this, right? So the left-hand side of 8.2 is symmetric with respect to the three variables, but the right-hand side is not. So having a graphical model forces us or implicitly chooses an ordering where we might have the same set of nodes with general dependencies, but the ordering specifies basically the order in which we models each node and measures each node, and that also has implications. In here, 8.2 implies that, for example, variable A is easy to measure, and C condition on A and B is easy to measure rather than the other way around. Okay, we'll talk about ordering a little bit again. So I'm just reading a question from week09a. Is there an application for, say, garbage collection, this kind of influence to possibly optimize for deleting variables and inferring if they might not be used anymore? Thanks for the question, right? So I am not an expert in garbage collection, but I know you guys have all had exposure from Steve Blackburn and his co-authors. Good question, right? So I don't know a definite answer, but here's how I would think about it. In things like garbage collection, the question, of course, the computation needs to be a lot faster than real time. Then the cost of building up graphical models and the inference costs should be taken into account. It's probably non-trivial compared to those. But let's just set computation aside, assuming we can do this and really fast. The question is what kind of state inside that kind of decision making is random, and what kind of factors we should just directly read off the different parts of the programming language stack and assume they're not random. If most things are not random, then maybe we don't need a complicated graphical model. But on the other hand, even if one of two things are random and cannot be or should not be measured, maybe graphical model actually has a role. I do believe this basically systems and machine learning, the intersection of these is a growing area. And it is quite underappreciated by, I guess, students looking for projects too. Because as a general observation for the CS department here, people who work in machine learning and AI gets lots of emails saying, I want to work on machine learning, computer vision, and NLP usually, but the system area and cybersecurity and so on are underserved. For also this reason, I have decided to make the guest lecture of this class to talk about cybersecurity. So remember to turn up next Wednesday. Better in person, but if you cannot, online is fine too. We'll advertise that again. So more generally, we can basically generalize this 3-node graph to have a general decomposition over any distribution over x1 through xk, k variables. The graph is fully connected, right? So there is a link in either direction between any pair of nodes. Right. So it doesn't save anything, but there is a direction where the direction is non-true. Like, so let's say if there are four nodes, so we can mention this, and then this. Right. So this is a fully connected 4-node network. A, B, C. So it's fully connected in an undirected sense, but it does impose an ordering. But you say, right, this is doing fully connected graph is, of course, not with the goal of using the language of graphical models. Here is an example of a 7-node network that has a lot less connections than a fully connected, its fully connected counterpart. So if we just read off the joint distribution, so basically if we have a graph, it's basically we can try and read off the joint distribution from the arrows, right? So in here, we read from the source of the arrow in general to the sink of the arrows for the whole graph. And the base network is always directed on acyclic, so it's a directed acyclic graph. Therefore, there is always a place to start and it will end, right? So, so possible to find at least one starting node, right, where it doesn't condition on anything else. In this case, x1, x2, and x3 are starting nodes. There's no arrow pointing to them, so therefore we write the 3 of them here. Just marginals on their own. And then for x4, it's conditioned on all these 3, so we write that. For x5, it's conditioned on x1, x3 only. X6 only depends on x4, and then x7 depends on x4 and x5, right? So for example, this particular click is, right, so it's this. So it's x7 have 2 incoming arrows. So this is simple, right? So otherwise, if we don't have this graph, then factoring this, if we say, oh, we define a joint probabilistic distribution as follows, you can see that going from the joint to the factorized is it's not obvious, right? It's only 7 variables. It's not like hundreds or even thousands of variables. So what is worth noting is that in factored joint distribution like this, it is the absence of links of the graph that conveys the most interesting information about the properties of the class of distributions that the graph represents. In order to see this, we can think about, and so compared to the fully general joint, where if we have committed to the same ordering, we would have P of x2 given x1, right? So if that's the case, there would have been an arrow here, but there is no arrow. That means x2 does not depend on x1, and that's useful information to know. And that's basically knowledge that's being modeled. So how do you draw a graph if you're given a factorization? So we draw a node for each conditional. So basically, each random variable gets its own node. We draw an edge from each conditional distribution associated with random variable to all the other conditional distribution or condition on this variable. So this is a mouthful. Basically, for each conditional distribution, we draw an edge from a variable that's being conditioned to the variable on the front that we're conditioned on, right? All right. So we covered basically, right in here, going from joint distributions to graphs. Basically pick up all the variables and then draw edges. And from the graphs, the other way around, to the joint distribution. Basically, we already walked through it once. So here are the two main steps, right? So there is a term for each associated random variable. Using Bayes' rule, each random variable is on the front of the conditional once and only once. And then add all its parents to the back. So only parents, grandparents don't count. For example, x7 is only conditioned on x4 and x5 and not x1 or x2. So, and each of these steps correspond to these. There is a corresponding step to convert the joint distribution to the graph. Yes, good question, Qingyu, and good answer, Taylor. There. So by definition, Bayes networks, or basically directed graphical models, they are directed acyclic. So we cannot have circles. Otherwise, we won't be able to factor. So we can restrict our, we are restricted to only expressing the joint into graphs that doesn't have circles, because that's how Bayes' rule works. It's not true in general for graphical models, as we will see next time on Wednesday and next Monday. So those two hypergraphs all have circles. Right? Yes, here is the formal statement. Only directed acyclic graph is legal. There's no closed path in the graph if you move along the edges. Otherwise, it's no longer called Bayes' rule. And the fact that there is no loops or circles in a directed fashion, that means there exists an ordering of the nodes such that there are no edges that go from any node to any lower number of nodes. Basically, according to the convention of this book, the nodes that don't condition on anything else are lower numbered. So there is, yeah, we can't have this. Otherwise, it will be circles. Of course, in some other books or papers, the convention might be flipped, right? So for now, we stick to the convention that we start from lower number nodes and move to higher number nodes. You may ask, right, can we have variables or set of more than one variable or vectors at the node? The short answer to that is yes. That just means if we have a set of variables, that means they share the same dependence or independence relations with other nodes. Okay, here's a notation note, right? So if we're trying to express a Bayes net using, of say 100 nodes, you can imagine that both the graph and the joint probability distribution gets pretty complicated. In graph theory terms, we can simplify the notation saying that the joint probability of k random variables is simply the product of k terms with each random variable conditioned on the set of parents of xk, where the set of parents can be empty, 1, 2, or many. So the graph is dense or fully connected if the set of parents is basically from x1 all the way to xk minus 1. When it's not that, it means we now have some sparsity in the graphical models, and then p of x is no longer general. And then there are assumptions like this, where you can drop some of the variables from the conditioning. All in all, these are all different ways of saying we have encoded conditional independence. All right. Fei Yang asked a question where I'm not exactly sure whether you're referring to something general or not. In general, no, but yeah, if you unroll the Bayes rule on that one, in general, no. So don't know where B went. If you refer to something specific, then ask again. Right. Okay. So there is a question about normalization. The answer is actually yes. So these are valid probabilities. So therefore, P of X summed over all the possible variables should go to 1. Right. So how do we do this sum? Which is actually a crucial question for computation, is that we know that this sum is over k different variables, over a product of k terms. We should verify this, or when we actually marginalize over different variables, we should find, for example, the node, again, from lower numbered nodes to higher numbered nodes. Right? Says there's always a node with no outgoing edges. Actually, so what it does is the converse, right? So marginal. So start from a higher number node. So this is according to the convention here. When the node is highest number, then there is no outgoing edges. We can basically marginalize over its conditional probability, and by definition, that's 1. And then we pick the next highest number node. By definition, that term goes to 1. And if we keep doing this, we can verify that P of X properly marginalizes to 1. This kind of technique is useful when we talk about computation, which we want today. So let's just stare at a number of other varying, a few different examples of graphical models to build a better intuition. And then we'll formally talk about d-separation. Okay, I won't follow up on the chat yet. Right, A and B are conditionally independent. I'm sure we can work this out offline, but let me know, or ask me afterwards. So it's always good to connect to something we know. So if we consider Bayesian polynomial regression model in section 1, well, basically, so T or Y is roughly W transpose phi of X, where phi of X is polynomial of X. And then T is Y plus some epsilon noise. So we can represent this because it's Bayesian, the W's, the weights are random variables with a prior. and we observe our data set. We observe T1 through Tn. Right, we can of course write it this particular way. We have a W, and X and Y are, X is non-random, so it doesn't appear in this picture. Therefore, T depends on W, and each of the T depend on the same W. But that's how we do learning. So we can write it this way. T1 depend on W, dot, 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 Tn also depend on W. But that's also a mouthful. One handy way of expressing n copies of variables that share the same structure is this so-called plate notation, where you enclose this variable t, or the part of the graph that are being copied n times, and then just draw one arrow rather than n hypothetical arrows. So in fact, the plate notation was invented by one of the ANU/NICTA alumni, Ray Buntine, whom I had the pleasure of co-authoring with. And then it's made popular by what's called probabilistic topic models for text, or latent dirichlet analysis. That was quite a nice model that are still in use. I've recently used it. Anyway, so let's look a bit more on polynomial regression. So this is, we could also expand this graphical model to include the other things that are in consideration, right? So you could use small solid circles to encode deterministic quantities, things that are observed and non-random. So note that this part, like W pointing to Tn, and copies of Tn is the same. And now we can see this picture is now clearer, because the picture before you might ask, hey, where is X? And it's sort of hiding lots of details. This is correct, but it's hiding conceptual details that might be useful to express, right? So you can say that X also has n copies, but it's not random. So, and T depend on X as well. Moreover, T depend on sigma squared, the noise variance, and W depend on alpha, which is again a known hyperparameter, a prior parameter. So this is, I would say, a pretty sensible representation of regression. And moreover, for the training task, we can say that, oh, the Tn's are observed, therefore we shade it, and then the W is not observed. We aim to infer its posterior distribution given the T's, and that's how we do, say, Bayesian regression. So this was a familiar task expressed in graphical model language, which makes like all the dependencies quite clear. All right, I'm going to skip this particular slide. Read it if you're interested. What else does the graphical model allows us to do? So once it's specified, or the conditional distribution being specified, we can actually generate samples from this joint distribution. So we basically walk through each node from low to high, draw lower number of nodes, the parents, and then draw the next node with values of its parents fixed. And in this case, if we would like to sample from marginal probabilities, then we just throw away the nodes that are not being marginal, like that doesn't appear in the final marginal distribution. Okay, Taylor asked a good question. Is there any difference between latent and hidden random variables? I would say they are mostly just different names for the same thing. sometimes you use one or the other because in the latent, when you refer to something as latent, you often mean that it is of interest and you possibly want to infer its values. When it's hidden, but whether you actually want to reason about it is not clear. Fei Yang asked, right, when the arrow goes outward and the node is observed, in general, no. Like specifying the direction of the arrow and whether a node is observed is not, yeah, there is no fixed relation there. But it is usually more convenient to specify graphical models as this is what we're about to get to. In a lot of cases, when we use graphical models, the higher number nodes are observed, the lower number nodes are unobserved, such as in the image segmentation case, right? So if we have a model of the physical world, it is the object and its position and orientation that determines the image, but it is the image and image alone that is observed, and then we try to recover these latent scenes, which is very high. So in the case of the polynomial regression example, it is not a causal process, but it can be made so. Right, and another comment that addresses Taylor and Fei Yang's question is that latent variables, they need not have physical interpretations, although in a lot of cases they do. One example of latent variables that does not have physical interpretation is, say, if we're dealing with a mixture of Gaussian. And the mixture is like the variable z. It is a convenience because without that, we couldn't do sort of EM kind of inference nicely, but it doesn't always, like mixture Gaussian is used in so many places now. A lot of times it doesn't have a physical interpretation. This one we also skip, you can read about in the book. Because we really wanted to get into conditional independence and be a little more formal about this, we have known like basically how to convert between joint distribution and graphs, and this is, or basically directed acyclic graphs. But let's reason about, and as you guys have been asking and hinting about, what this hints on is conditional on variables, and which variables observed and latent are very important in thinking about Bayesian networks. So there is a chunk of content talking about this. So let's see how far we get. If we don't manage to get to it and get through this chunk, we can continue to, on Wednesday as well. So if there are 3 random variables, A, B, and C, and this came out in the questions earlier, and the following holds, right? So when we condition A on the 2 of them, B goes away. Like A is only dependent on C, and like, so this is called A is conditionally independent of B, given C. And there's a notation for that too. So this is the independence, probabilistic independence symbol, A independent of B, but there is this statement don't hold in general. It is given the value of C, A is independent of B. Right. This equation must hold for all possible values of C. If there's, if it only holds for a subset, you could do like condition on C equals to 1 or things like that. But the consequence, but if it holds for all possible value of C, we can do things like this. P probability of A and B given C can now be written as probability of A given C and probability of B given C because of conditional independence. And what kind of graphical model does this imply? We'll have C on the top and A and B at the bottom. So the conditional independence simplifies the structure of model. In this case, it loses an edge. So this edge no longer exists, right? And you can save some computation as well because of the marginalization trick. And note that conditional dependence is a related but different concept. And yeah, let's not talk about it. Someone talking about this one way is a lot easier than the other way. Interesting, right? So conditional independence satisfies a number of basic properties such as symmetry, decomposition, and so on. I'm not going to go and show you or prove these. You can, yeah, these can be proven using essentially manipulating the joint distribution and Bayes rule. And you're not expected to remember all of them either. If you need to use them often, you will remember them. But symmetry is a sort of an easy one to remember. Okay, so let's have a hard look at 3-node graphs in order to reason about some of the general patterns. So the immediate goal is to infer the conditional independence between A and B. And the larger goal is to spot some general subgraph patterns so that we can say useful things about them. So if we have this graph, which we just drew on the last page, we can say that if, so A and B are not in, so they are not in general independent if we don't condition on anything. And this picture, according to our language of shaded nodes being observed or can be conditioned, that can in turn be conditioned on. So if C is unobserved, A and B are not conditionally independent. This is pretty much the same what we have been just said. On the other hand, if C is observed here, we know that according to this graphic, A and B are conditionally independent. So what did we just say? We just converted, we already know how to convert between this expression and the graph. And now we just introduce the language of conditional independence. Elaborate it and essentially say the same thing using this new language. All right. And this says A and B are conditionally independent given C. All right, moving on. In general, this the general graph subgraph patterns of this kind of 3-node structure is called a tail-to-tail structure because C, the node C, is being conditioned on or not, and there are two tails of the directed edge connecting to it. All right. So the general statement we can make is conditioning on C blocks the path from A to B. And that equivalently means that A and B are conditionally independent on C. All right, so this is, now we reasoned about the 3-node graph, introduced the new terminology, and made a general statement. What about a different pattern, right? So now that we've introduced the tail and tail pattern, you will say, Oh, right. What about head and tail? So this, in this particular example, we can draw the head and tail pattern of C easily as the 3-node network as well. So basically, well, one other node points to C and C points to the third node. We can see that conditioned on nothing, A and B are not generally independent. If C is latent, well, A and B are connected anyway. But on the other hand, if C is observed, A and B are conditionally independent. To see this, we manipulate Bayes' rule by saying the joint probability of A and B given C can be expanded like this using Bayes' rule. And then the top part expands into P of A, P of C given A, P of B given C. So this is from the graph. And then we look at this too. So the first 3 terms here, using Bayes' rule, converts to this P of A given C, and therefore we conclude A and B are conditionally independent given C. All right, so that's head and tail pattern. That's quite similar to tail and tail pattern. You would say, what does this leave us? So note that there is no tail head pattern, just because, we can call any node, like basically swap the label of A and B. Then we get the tail and head pattern. So the tricky thing is the head and head pattern, where C is the node where 2 arrows is pointing into, or 2 or more nodes are pointing into. So if C is latent or unobserved, we first write out the joint as probability A, P of B times P of C conditional on A and B. So if C is unobserved, we marginalize over C, basically we sum over C. We can see that summing over C has nothing to do with these 2 terms. Therefore, we can move it to the last term here, and that marginalizes to 1 because it's a proper conditional probability. So therefore, probability of A and B, the joint of A and B equals PA and PB. And so what this means, despite there is a graphical model, if C is latent, then A and B are conditionally independent. Okay. What happens if C is observed? This is a bit tricky. So let's do this by unrolling so this is the graph. And then we try and manipulate this right now. Basically, if we expand this using Bayes' rule, and then we can basically compare to the left-hand side term-wise, we can see that they're not equivalent. So what this means is A is not conditioned on B, conditionally independent of B, conditioned on C. This is a mouthful, and we'll explain this in a little bit. Let's first summarize this general pattern, right? So in both graphical models, there is a path, undirected path from A to B. Basically, A and B are connected. The node C is called head-to-head pattern. And the terminology says basically the unobserved C blocks the path from A to B, and A and B are becoming independent. So it's this case. And the presence of the head-to-head node in the path left makes A right. So when C is observed, conditioning on C unblocks the path from A to B and renders A and B conditionally dependent. So that's quite counterintuitive, right? Unlike the other two cases, when you observe them, the middle node, the two other nodes become independent. Here it's a converse. Furthermore, let's talk about this extension case, and then we'll talk about the intuition. Spare me with me 1 second. So as we can see, there's a head-to-head pattern here as well. Furthermore, if some descendant node of this head-to-head pattern node is observed, it also unblocks, in this case, A to B, or A and F. So and head-head path will become unblocked if either the node or any of its descendant is observed. So this particular phenomena is called explaining away. So let's walk through a new example, but I left this exercise. So do like reason about this using the wet grass example in the beginning, right? So basically, condition on the grass being wet. What does it mean about sprinkler and rain? So let's just look at a slightly different example. It's just the same statistical phenomena with variables of different name, right? So here is a simple graphical model of a car, let's say my car. So electric fuel gauge is G, right? It's a gauge, and then it's battery, and then this is fuel level, right? So if the fuel gauge is giving me a warning, or it's showing the level is low, it could be because usually I drove a bit in the last few days and it's out of fuel. But in rare cases, it could be that the battery is malfunction. I forgot to turn the light off. So not knowing the status of fuel gauge, then whether the battery is functioning well and whether there is enough fuel are independent. These are driven by two physical processes and they don't affect each other. But if I observe that the gauge is, let's say, showing a low reading, and I know that the battery is functioning normally, then this increases the probability of the fuel being low. So in a sense, what this phenomena comes about is because of the two competing causes for an observation in a variable, sort of, if we know one is true, the other one is less likely to be true. Let me see if this, okay, the book has a full write-out about this example. On the other hand, right, if I observe gauge reporting a low reading, and I know that if I just topped up fuel today, then there is very likely that the battery is malfunctioning. In fact, so we as people reason about explaining away all the time, like basically rule out factors one at a time. And in the BaseNet, it's basically a more formal way of recording this. Let me leave it at that. If it's not clear, shout at me. So we will basically walk through what we just said before we conclude. So we established conditional independence for all configurations of the three variables, head-head, head-tail, and tail-tail. So head-to-head is the tricky pattern. The other two are basically when it's observed, it blocks the path. And we talk about the variable in question being observed, condition on, or unobserved, not conditional. So we say that the head-head junction with observed descendant, it's tricky. It's a bit subtle. What does this subgraph pattern allows us to do is that we can now generalize these results to arbitrary Bayes nets. Roughly speaking, this means that the graph connectivity implies conditional independence for those sets of nodes which are directionally separated. So this is just a name. The reason for introducing a new name is because it's slightly shorter than saying inferred conditional independence with a set of like observed variables. And it has an even shorter name called D-separation in the graphical model literature. Right, so again, it's the same thing, but using the new name. So a blocked path, so D-separation depending on this another notion called block path. A block path in the Bayes network is a path that contained an observed head-to-head or head-to-tail node, or an unobserved head-to-head node. Basically, these three cases that we saw twice in the last little while. So if it fits any of these three, the path is called blocked, and A and B are conditionally independent given C, right? Or given the states of C, not given the value of C. Given C is unobserved here and C is observed in the other two. So how do we reason about these separation for a graph in general then? So here comes the generalization. We've been using small case A, B, and C, but now we are saying that the big A, B, and C are arbitrary non-intersecting sets of nodes. So this is a powerful generalization. We already said that on each node, we can have a set of variables. Moreover, each node can be a subgraph in this case. And there can be other nodes that are not contained in the union of A, B, and C. And we consider all possible paths from any node in A to any node in B. Right. Something like this. So we have a set of nodes called A, another set of nodes called B, another set of nodes called C. They're all non-intersecting. And now we basically look at all possible paths, right? There might be some paths going this way. There might be some paths going this way. And there might even be paths going this way, right? So we consider all possible paths if it fits any of the patterns we mentioned, then such path is blocked. Basically, then restate the pattern again. If the node is head-tail or tail-tail, and the node is in set C, or the node has a head-head pattern, then neither the node nor any of the descendants is in set C. And the set of nodes A is conditionally independent of B, given C if all of the paths are blocked. And we call A is D-separated from B by C. So the way to denote the head-to-head separation pattern is that we assume the nodes in C are observed, and in order, like the head-to-head pattern needs to have the node unobserved for the path to be blocked, so that for the head-head pattern, meaning all head-head patterns between A and B, the node needs to be outside. This is outside of C. All right. I hope this makes some sense. Basically, in order to generalize what we just said to sets, we just consider all paths, and if all possible paths is blocked, then A and B are conditionally independent. So also by definition, this means we cannot have a direct edge from like nodes in A and B to B, then they're not conditionally independent. All right, so here are some examples. So in this little example graph that we saw before, like A, B, C, E, F, the path from A to B is not blocked by F because F is a telltale node and it's unobserved. When it's telltale, it can be it blocks the path when it's observed. And the path from A to B is not blocked because this C is observed, but its parent E has a head-head pattern. So that's not good. For the same graph, if we change the shading from C to F, then it's blocked because, this F blocks this path, and then the unobserved C and E blocks this part of the path as well. So the path from A to B need to be blocked by both variables. In this case. TU's question, yes, we care about the direction of edges, and I think it got clarified by Vikram. Thank you. So we have, in the first half of the lecture, we've been talking about converting between factorized joint distribution to graphs and back. So what we just talked about is a language that allows us to convert between factorization and conditional independence. So it goes like this. If a probability distribution factorizes according to a directed acyclic graph, and if A, B, and C are disjoint subset of nodes, such that A is d-separated from B by C, then it is conditionally independent. So basically, this theorem establishes the link between being d-separated and conditional independence. The converse is also true. If a joint distribution satisfies the conditional independence implied by this separation, then it also factorizes according to the graph. So why do we want statements about this? There are several closely connected notions that represent more or less the similar intuitions. So the reason we care about this is that conditional independence statements is what we can usually get from a domain expert, a person designing the garbage collector, a doctor, a network engineer trying to troubleshoot a printer, and so on. So they may know they need a model of P of X for computation, but they are not the one usually doing the computation. So they provide the conditional independence, and that converts to a factorization. And then, for example, we, the machine learning engineer or researcher, designs the computation. So then one can build a graphical model for computation from these local conditional independence statements. All right. Yeah, let's wrap up this part with another general statement. So the graphical model, basically a set of nodes with arrows with forming a directed acyclic graph, can be seen as a filter on the set of joint probabilities, the whole set of joint probabilities, right? So the book says we can view a graphical model, in this case, a directed graph, as a filter that probability distributions P of X are allowed through if and only if it satisfies the directed factorization property or with associated conditional independence and d-separation relations. So if we call the set of possible probability distributions P of X that pass through a particular graph as a filter as DF, due to the theorem on the last page, it says it's the same set of distribution DF that will be allowed through this. Basically, it says, well, the DF implies the graph, and filtering P of X using the graph implies DF. So, which is to say that the language of graphical models is like a necessary and sufficient condition for the set of conditional independence that we want to model, which is to say that this Bayesian network language is quite precise, and that seems desirable in many occasions. So that's it for today. I'm going to pause and read off if there's any questions for 1 minute, and then we'll move on to the quiz. Right, so directed edges and non-undirected edges. So more, yeah, I agree with so this Chinyu's question, I agree with Vikram's answer in general. So yeah, that we write out the factorization of the joint distribution, essentially following the direction of the edges. What becomes sometimes a little counterintuitive is that when we reason about d-separation, these patterns, sometimes they are seen to be like sort of going against the arrow of the edges somehow. But in that case, we just look at the directed subgraph as a pattern rather than saying we're following the edge to do something. I hope that helps. So for this particular reason, as we will see on Wednesday and Monday, so a general procedure for doing inference on Bayes nets, conditioned on the arbitrary set of nodes, and then we want to get the distribution of another arbitrary set of nodes, we first convert it to undirected, and then use the factor graph procedure. So ensure that there are inference procedures, there are common inference procedures that ignores the direction of the edge. There are also other inference procedures that make use of the direction of the edge, but we're not going to cover that in this 3-lecture span. Then the literature of graphical model is fairly large and huge. So even with 3 lectures, we're only going to cover the tip of an iceberg to an extent. We're not going to talk about, for example, approximate inference and graph cuts and all that in this particular lecture, although your computer vision class might touch upon some of those. So those are related, right? How to do inference in Markov-Lenin fields and what to do if there are loops, lots of loops. Is there any guarantees in graphical model inference and learning? But right, having seen this language of graphical models at least once, it will give you a way of comprehending these more advanced inference procedures and modeling the models. That's that. Yes, the previous question about generalization. Thanks, Feiyan. Let me do quiz first and then do the context switch. So while giving people to think about whether they have other questions about the quiz. So this is a histogram. I guess since it's posted, you can all look at it. The mean and median are like somewhat here. The variance is fairly large, as typically in any grade distribution. The easiest question were confidence inequality. So people seem to have done generalization well, or that question is sort of the options are sufficiently unconfusing that it's easy to guess. Not sure which. The hardest question, or the most confusable question, is this particular one. Let's read the question. So the question is about kernel density estimation. So about, yeah, the score rate for this is 23 to 25% across the 253 entries we have. So we would like to estimate density on the infinite space using kernels. So I think we got a question about what about density in the infinite space. I pretty much said the computation is local, don't care about that here. So you will see. So the point pattern, the observed data point, sits on the regular grid. Basically, the origin has no point, but there is basically one point in each of the 90-degree position, and then for each point, there is another point at plus or minus 2 on either direction. And if we extend this like infinitely, we get the pattern like this. So there are two kernels that are being used. One is called the cube kernel, which is a constant if it is sort of, well, one thing is about the like Manhattan L1 norm of a particular point, right? So what is L1 norm? In 1D, L1 norm is, let's say we have x0 here, and we have x0 plus 1 and x0 minus 1. So L1 norm is simply the distance to the point. In 2D, if we have x0 here, then x minus x0, the L1 norm being 1, it's like all L1 ball is this diamond shape. Basically, when it's on the axis, we can verify this is like the distance is 1, and then at this point, it's basically x0 plus a half and a half. Okay, with that out of the way, what we are looking at is essentially the cube kernel will be non-zero within this ball. Okay. Let's say if I center on this point, first kernel will look like this, and it's sort of flat. And the pyramid kernel is also within the same shape. If I center it on this point, it basically says when the L1 norm is less than 1, then it is 1 minus that L1 norm. When it's larger than 1, then it's 0. So it's also being constrained on this. It's called the pyramid kernel because its highest value in here is 1. And then the value on the four corners is 0, and the value on the edges are the 0. Basically, value in here is 0. You would say, okay, then what's different? So after drawing the shape of these two kernels, you will then notice that one is called cube kernel because it's this diamond shape, but it's a flat top. And moreover, if you draw this for more than one nodes, you will see that they are connected. Right. So it's a flat top and connected. So all the values are pretty much the same. But for this pyramid kernel, we basically have the value more like a triangle. On 1D, the pyramid kernel would look like something like this. And then connected to the next point will look something like this. So it drops down to 0 and rises towards the next point linearly again. So with this picture in mind, looking at these options, so P2 is continuous everywhere. Yes, it's continuous, it's not differentiable because it drops down to 0 and rises back. So this is correct. It says P2 is larger or equal to P1 everywhere, which is not correct because this largest point is 1. With this one, the largest point is 1 over square root of 2, so it will drop below that, somewhere in the middle. Both kernels are computed from data points within the circle in the Euclidean space. No, it's the L1 ball or L1 circle, which is like a diamond shape, not the L2 circle. It says at the origin, P1 is greater than P2. Actually, so this cube thing is weird. It drops down to 0 at exactly the boundary. So it's and it's not strictly greater than. At 0, 0, they're both zeros. So they're actually the same. Okay. So that's about the quiz. I hope it gives you some taste about what kind of questions or how can you use what you learned in the lecture slides in order to reason about different things. I would also say that most of these quiz questions, I remember maybe 6 or 7 out of the 9 are last year's exam questions. So that means you have some answers for last year's exam, which will be shared in its entirety pretty soon. And this year's exam preliminary is scheduled on 3rd of June if it doesn't change again. So you will see some Piazza post about that soon enough. I would say these these questions are not particularly easy, constrained by the online examination format and so on. But they are not super hard either. So hope that helps. And now let's go back to Fei Yang's question about generalization. I can scroll up and show myself. You asked. Into my Teams. It's very slow. Right. Okay, let me try and find what you're asking for. Generalization. Said the loser bound is only a 10 if delta is less than a half. Do you refer to this slide, Fei-Yang? Yeah, okay. You're giving me a screenshot. Yes, okay. I got Kylie and Taylor's question. We'll get to that after this. me first find where that is. I'm looking at the. Here. In general, we want delta. We assume delta is not great enough, because otherwise we could flip the classifier. Okay, I'm back. Not sure what happened on the laptop. It cut me off. I hope people can hear me. If so, give me a thumbs up.
Yeah, we can.
Yep, thanks. I'm afraid that I still don't feel I understand the question. Are you referring to getting rid of the 2 at the bottom of the?
So in the previous slide, in
the
slide
equation
where
in the green circle in green.
Oh no, in
or something else.
In the previous slides, 2 scaling regimes, right? It says there's at the bottom there's a looser bound where 1 minus delta, 1 divided by delta is greater or equal to 2. So I assumed that was in the previous slides.
Or the or is that related to the one-sided or two-sidedness of the? Oh, right.
Yeah, this slide at the bottom where it's the loser
think
bound.
what you're asking is. I try to explain this in this particular slide, right? Where we essentially cross out the 2 at the end. Okay, Feiyang. So I'm just going to work over this slide a little bit as a possible answer to what you're asking. If that's not what you're asking, let me know. Yeah, so.
Yes, so my question was.
Yeah, I would say the way that ML Storybook
in the slides that
this particular bound, yeah, it's a bit different than many other literature does, where it doesn't seem to invoke the two-sided of things immediately, and then a lot of things in the literature essentially just didn't carry the square root of 2 on the bottom, and the way it was done was to basically first invoke the two-sided and then assume. Right. Right. So in this particular slide, I did say that if we assume delta is we assume delta is less than a half. I don't remember on top of my head how this affects your calculations, possibly for question 1. So if you're asking about that, I might need to get back to you afterwards.
Yes, so yeah, I just think that without the looser bounds,
you can drop the
right?
twos in those. If you're okay with it, I'm not sure how much that helped. If it doesn't clarify, then let me know and I can either get back to it after or something. So let's talk about the quiz, the Hoeffding's equation, and the calculation, and question 6. So let me ask my computer and see if it will show me the question, and then I'll share screen there. Seems I should have. It's very slow. Should have a copy of the quiz saved as well. Took me a while to export last year's exam and save that. Okay, now we have the quiz. Do preview. Okay, there we go. Share screen. Okay, you can see my screen. So first of all, question 6. Expectation maximization for the mixture of Gaussians can be alternatively described as probabilistic k-means. That is the correct answer. In the class, we went through a bunch of connections between GMMs and k-means. So k-mean minimize an L2 loss, mixture of Gaussians minimize the or maximize the log likelihood, but it's the interpretation, the connection here is basically it's k-means with a flexible covariance function that's being learned, and also with probabilistic assignment of points to the cluster centers. Probabilistic linear regression, that's not true because it's not a regression task. Probabilistic PCA, that refers to something else. We're not doing dimensionality reduction in particular. Probabilistic linear classification, that's again not true because we don't have the target. And then probabilistic supervised learning, that's not true. Again, no target. Just a bunch of data and we want to minimize some distortion or likelihood function. So the next few requests. So the Hoeffding's equation. Okay, this is interesting. I did go through it. I'm not sure I've written it down in a way that I can share it with you, but let me look. Oops. No, I forgot where I wrote it down. So basically, what I was looking for. Right. Let me try this. So for the whole things, I will need to do some sketching. Yiran requested if we do Q2. Okay. Yeah, maybe we'll talk about Q2. Sorry about the back and forth because I can only do sketching on the iPad, but I can only share the water screen on the computer, which is quite confusing. So in order to minimize the switching, which takes a bit of time. So question 2 first. So we want to, well, we're doing classification, and the class labels are -1, +1. And then we ask about what the shape of the classification boundary is. Right. So option A, again, depending on which version you see, the options are randomized, as you will all realize by now. And in the final exam, the questions will also be randomized. So what the questions you get will be different from your friends, which I hope helps for us to trust the exam a bit more. So if we assume cross-conditional probabilities are Gaussian, then the decision boundary is a hyperplane only when these Gaussians have the same covariance matrix. It's not true in general. If we use the perceptron to learn a decision rule, then the decision boundary is linear. This is true because perceptron is essentially one linear neuron, yeah, right. So it's a one-layer neural network with a step function as the activation function. So if we use a one nearest neighbor classifier with Euclidean distance, then the decision boundary is piecewise linear. This is true because is there a picture about it? Let me find what. And right, so D is also true for logistic regression. The decision boundary is where like the posterior of Y is 0.5 with the 0, 1 coding. So we just need to convert a -1, 1 to 0, 1 coding. Then the decision boundary is a hyperplane. That is true. So with the one nearest neighbor, try and recall where we talked about it. Right. Chapter 2, the last subsection. In fact, right. So with one nearest neighbor, the partition of the space end up being what's called Voronoi diagrams. So figure 2.27. You can go there. So Voronoi diagram is basically, let me see, I believe it's in our first kernel lecture. I can pull that up. Go and share screen. Wait. This picture. This picture. Huh. Right, so somehow the PDF picture is a bit broken. If you have a physical copy of the book, let me see. Doesn't focus. Maybe. Anyway, 2.27. Right, so this, sorry about being like the PDF being broken. Green boundaries here. Right, so just to for a bit more context. So in the book, there's a whole bunch more red points on this side and a whole bunch more like blue points on the other side. And this green boundary is basically a subset of the boundaries of so-called Voronoi diagram, where the whole space in 2D is partitioned into, say, a set of cells, where within each cell, so any point within each cell, its nearest neighbor is the point in the center. So for 1 year, like Voronoi diagrams are like polygons in the in an n-dimensional space. Therefore, if we pick a subset of their boundaries that are connected, it's piecewise linear. It's easy to show that they are sort of Voronoi diagrams are polygons because at any given point, you like the boundary is basically the dividing spot, like the equidistance line or hyperplane between 2 points. All right. Okay, back to the Hoeffding's calculation. Right. So what we did was we inherited this particular example and then asked you to plug in this instead of a separate example from a person's height. So let's just convert the two scenarios by, let's say, we copy this bit here. Right. Okay, so all right. So we wanted to apply this one to this example. Binomial. What we want to do is so for essentially 16, like x greater than 16. So right, what we need to determine is n and t. So t is the discrepancy of the observation versus the expectation. And then the sample mean here is actually for the binomial. The sample mean here is, the observed mean is 16/20, but the actual mean is 0.2. Right, so t is 0.6. The discrepancy from the actual mean versus the sample mean. And then 2t squared, right? So then what I did is just plug it in. So it's x of minus 2 times 20 times 0.36. That question. So 2 of the options in there, right? Okay. So 1 over 45 is on the example. That's an easy rule out. And then another easy rule out is the true probability. Right. So it says the actual probability that this happens is 1.38 times 10 to the minus 8. And this bound, right, so it cannot be less than that. So that's another easy rule out. And then it's a matter of just plugging in the number, and it's option D on my screen, which is the one that's 10 to the minus 6. And not 10 to the minus 7. That's that. Does this help? Okay, yeah, Yiran has a and Qinyu has a couple of follow-ups. Let me do that. Right. Okay, I hope the right. Okay, Kylie seemed to be happy with this particular calculation. Okay, I'll go back to question 1. Qiyu and Yiran asked about hyperplanes or linear. So yes, the hyperplanes are the terminology for n dimensions. Linear separator, well, we say it's a line when we're only talking about a two-dimensional input space. So in high dimensions, technically it's a hyperplane because it's no longer line anymore, despite we also say linear classifier that refers to the linear combination of inputs, but then the separating, like the estimated class boundary is called a hyperplane. I hope that helps a bit, maybe. About why the Gaussians need to have equal variance or covariance. Let me go back to classification. When we talked about this, there was a picture. Here. Right. So this particular picture shows the input a two-dimensional. The Gaussian mountain encode the conditional, like the class likelihood, and then so where this picture crosses from red to blue, or 0.5 in the posterior probability is where the separation happens, and the book claims that it is a line. Can actually verify it. Furthermore, the book also has this example where it has Gaussians with non-identical covariance matrices in 2D, right? So the red and green have identical covariance matrices, and the blue is just the same thing but rotated, make them unequal. So the boundary between red and green are still a line, but the boundary between the green and blue and red now are quadratic curves. If you remember from high school geometry, which can be a while ago, yeah, basically if these are, yeah, if we intersect, so these are conic curves where if we cut the cone, or we can get all of these quadratic curves. We haven't derived what these expressions are. It's just stated in the book that, well, trust me, it's a quadratic discriminant. So it's, in practice, you can, without too much difficulty, derive it or draw it. Ask sklearn to generate this for you. But I suppose in here, what's important is the intuition when things are separated by hyperplanes and when not. When they are not, we don't quite care when the boundary is quadratic or not, since a lot of cases we operate in the realm of like kernelized models or neural network where the separating boundary can be anything. Okay, let me have a quick look at question 1. Yes, surprisingly, this one is actually, yeah, it's the average of the question, the true-false question is not so, not so high. Yes, it's worth talking about. It says, I'm not going to share screen again. The goal of principal component analysis is to interpret the underlying structure of the data in terms of the principal components. Up to this point, it's correct. And then the last part, that are best at predicting the target variable. That's not correct because there is no target variable. PCA tries to explain the data, but without a target in mind. There are projection methods with target in mind, such as the Fisher linear discriminant and so on, but we didn't really talk about them. I hope that helps. So that's all. We're at 2 o'clock, so I'm gonna wrap up. I hope quiz 2 sort of kept you thinking a little, and good luck with like the semester end deliverables from this class and others. We will provide more information and help about other assessments in due time.